So, welcome to the 5th chapter of our lecture series, Principles of Physics. And today I want to start talking about the big picture. How does physics work? What is special about physics? Why do we even talk about physics, right? So we've seen that physics has a long history, and it's a history of exploration. People have often tried to find a simple definition of what physics is, but it's always a bit complicated because physics can be many different things to many different people. However, if we want to understand physics, one thing may stand out. And that's maybe the first thing we should consider. The thing that gives people trouble about physics has a lot to do with mathematics. When you learn physics, it often appears first as an obstacle, something you don't like so much. But it's also a very powerful tool. And physics has been shaped by mathematics. So a lot of professional physicists would start from the idea that you can express laws of physics in form of mathematics. And that is not a trivial matter because our human experience does not come to us in the form of mathematics. So it takes quite an effort to adapt mathematics to the human experience. So I think it's a good point to start at, to think about the way that we can translate human experience into mathematics so we can develop physics. Physics always quantifies experience, and we normally start with the quantification of distance and time. Time and space, if you will. But in the end, we wind up with many different quantities. We went through thermodynamics, we went through optics. There are always different kinds of quantities that characterize different physical systems. So we need to consider how we get these quantities. And getting these quantities is normally called a measurement. So we are measuring quantities. And the measurement must be a procedure that is objective. This is actually a key point. What does objective mean? Objective for the physicist means that we know exactly what specific physical system the measurement refers to. The physical system is called the object. That is why we call this objective. It must be independent of the circumstances. So the value of a physical quantity should not depend on what the observer intends or wants. It must be the same in all measurements and under all circumstances. That is a very important criterion, and we'll come back to that later. So all measurements are based on phenomena that can be quantified. And to start slowly, you can first consider how you measure a length. That is very important. You hold some kind of scale, a ruler, next to the object. And then you compare the two. So seeing these objects is a phenomenon. And then you quantify the phenomenon by comparing the scale here to the length of the object. That is actually something you can generalize. Now in time, it's actually the scale on the face of a clock. Of course, nowadays we often do that digitally. So what's going on here? Well, very often we here have voltages inside. And we are also comparing almost in the same manner, electronically. So the concept can be generalized. We simply need a method to quantify by attaching a scale to the phenomenon. So I want to slowly develop this until we get to deeper and deeper issues. This is the starting point. We already talked about many different examples. So temperature is also a phenomenon and here we use a thermometer. So basically the same kind of scale on a thermometer where we evaluate how much a liquid extends, for example. Or we have an electronic thermometer that, like the electronic clock, compares voltages and then gives us this digital number. And even color is quantified by the amount it bends in a prism, which gives us in the end the wavelength of the light. So here we also have a quantitative phenomenon on the screen. The prism maps the color onto a position and therefore on a distance. Right? That's actually a very important key point, that we normally map things to each other. In the original development of physics, it was usually a physical scale of a certain length. And that's still a very good way to think about the measurement, because now we should be a little bit critical, a little bit skeptical, because it's still not trivial that we can attach a number to what we see. There's always a problem with scales. Right? Actually, there's a problem with the idea of a position. Do we really know where something ends or where something is? Because you can clearly see I draw something with a chalk that makes pretty broad lines. So I'm definitely not giving you atom size here. So, well, measurements are never exact. And it's good to remember that. The errors do come from our methods. So that is already a problem with objectivity. Errors originate from the methods. We have to think clearly how we quantify. The method of quantification gives us specific errors. We need to understand those errors, why they happen, where they come from. The first problem is the use of a scale. Any scale naturally limits the resolution. And that means that phenomena may actually look different on different scales. The mathematics easily gives you a point, but that is really a mathematical concept. You cannot find this point in your experience. So this is a logical problem. Again, I give you the example of the ruler. You now want to be very precise, and you look very closely at the scale. And here may be 24.0, and here may be 25.0. Then you will read off 24.7. But you are really between two ticks. You could try to estimate how far you are on which side, make another digit, but then you still need another digit, and it would never end. So you have to make some compromise at some point. And if you do experiment, you'd normally just give the error. For example, you just write honestly that you measured 24.7 plus minus 0.05. And that would be your resolution error. So this is a fundamental problem. The only way to quantify experience is by comparison with artificial scales. All our scales are normally artificial scales, certainly when it comes to space and time. So that's the first technical problem. But it's by no means the only problem. There is another problem associated with our ability to control the circumstances. It is clearly not easy to isolate an object completely. Most phenomena are not of the kind that you can identify exactly the one property of the object you want to know. So in most cases, external influences can also cause errors. And these errors change every time you measure. They fluctuate. That is actually quite important. In fact, it's almost the opposite, that you would not trust a measurement that did not show these fluctuations. They are so natural and so fundamental that you expect them in any non-trivial measurement. So a good physicist has to understand the statistics of the fluctuations. So you have to make several measurements of the same quantity. And you're probably familiar with this, because if you learn anything practical about doing physics experiment, this is a big part of it. You make k measurements, and you take the average as the best estimate. So let's say the quantity is m for measurement. The best estimate is the average. based on typical assumptions of statistics. You sum over all k measurements, 1 over k, all of the values, and you get the average. And here, the statistical error can be estimated by the variance. The variance is the square root of the average of the squared difference between the individual result and the average. And that's extremely convenient if you want to evaluate how good your measurement was in the statistics. So maybe I make a larger picture here, because you should get a bit of a feel for the way this really works. So I gave you an example, or I'll give you an example here that is similar to the previous one. I start from 24 on the scale and have a scale with smaller ticks. And here I have, again, 25.0, so this is just 24.5. And now I have one measurement result here, 4 measurement results here, 3 measurement results here, 5 measurement results here. This is basically a histogram. And finally, there is one outlier here at 25. And I can calculate. And the result here is an average of 24.6375. And the variance here is 0.1576. So you can check whether this corresponds to what you would have felt or guessed. First of all, the average is about here. So this is m bar. So how wide is that? You would normally have some feeling for how wide the distribution is just by looking at it. The exact delta here gets you a little bit beyond this tick and a little bit before this tick, and that is the region in which you expect the actual value to be. Note also that in some sense you could maybe get above your scale, because here you average. If you measure enough values, maybe you can get an estimate better than the scale. And maybe it's deceptive. You have to be very careful with reading out the data. Now, a lot of experiments that are actually going on with very difficult systems fall into this category. And what I want you to think about is that this is the foundation for finding laws of physics. Which means that you don't see the mathematics first. You see something that is much harder to understand. You're trying very hard to put patterns into that. So now comes the mathematics, which is also necessary, because without the mathematics, all you see is data. And data by itself doesn't make any sense. So you really need the mathematics to make sense of the data. Mathematics is a very powerful way of logic. But it's also very ideal. So to apply mathematics, we have to compare the ideal to the actual experiments. And then we see patterns. The data is always imperfect for all the reasons that I try to sketch in these two important examples of the scale and the randomness of errors. So even something that would be as simple as motion in a straight line is not just seen. You cannot measure every point on an infinite line, infinitely dense line, if you will. So even in one interval here, there would be an infinite number of points which would be impossible to observe. Yet you are satisfied with your law of physics, which gives you a function, simply because within the errors that you know, everything seems to lie on a line. That can be a bit dangerous because you could be seeing patterns that are not really there. So care must be taken. And here you really need some kind of theory because the pattern should be meaningful. A big problem is that there is never a one-to-one correspondence. In modern philosophy of science, you find that this leads to the idea that you cannot actually prove anything. And strictly speaking, that's true. You cannot prove anything because to prove something, you would have to use pure logic. And as soon as you make an experiment, that's not pure logic anymore. You must make some assumptions. And you must be very careful about these assumptions. Otherwise, the outcome will be wrong, or at least deeply flawed. Right? So this is a little bit of the challenge of the whole story, because you could think physics works by some kind of rule. You just follow the scientific method, and whatever you do will be right. But that would be highly naive. So there's more to it. And from this point on, I try to get to this thing that you also need, the concepts that you need in addition to organize the experiment you want to do. It's one point to get your thoughts together and prepare for the next step, because we really want to gain an understanding for problems and the challenges that face scientists. We see a lot of progress in physics, we see a lot of progress in science in general, but there's also a lot of doubt, a lot of challenges. And it is important to be aware of that. It's not just obvious that we have progress. It's not just obvious that we understand completely new phenomena. In fact, there's often the feeling that you should basically just assume that we already know the essentials and all we are filling in is the details. But that is not so easy. And what is often underestimated, because when you read textbooks that is actually given to you directly and much too fast, is that there are requirements. And here I hope I inspire you a little bit to think for yourself whether these requirements make sense and how you would apply them if you have to do your own work. Just in work-related things. You can apply them actually in very simple situations and scenarios where you try to find out something in what you could call a scientific manner. So if your observation is to be scientific, what do you need? I already hinted at it a little bit, yeah. So, but this is really the challenge for everybody who tries to do some science, and especially for students who start out, because you're always told this is an important topic, important field, and everybody is interested in finding out something. And you yourself may not be in that position where you think that's interesting, right? And nobody will explain to you because everybody is so busy and is inside their field. So it's very good if you can think for yourself. Because somebody who is already a professional in a field will not actually tell you very objectively what you should do or why this is interesting. So the first thing is really the object. So you should have a clear and unambiguous idea of what the object is. So you need an identification of the object. And that is harder than it appears, because normal lectures and books give you the object as if it was obvious. And it's normally not obvious at all. There are cases where it's fairly obvious, and I come to that. But number one, you need a clear and unambiguous identification of the object. Now, what is number two? You might say, well, number one is already pretty complete. But no, because every object exists in its context. So do you understand this context well? And in physics, that is actually a control of the conditions. So you need a sufficient control of the external conditions. All external conditions. And that is actually something that works mostly in physics. And you might argue that it tends to become a difficulty when you go to biology. It's definitely a problem when you go to sociology. Right? External conditions, when you're dealing with human beings, when you're dealing with living things, there is a limit to how much you can control external conditions. Right? Physics is normally focusing on areas where you control external conditions. So that's one thing. And finally, yeah, because of what I said in the beginning, physics is quantitative. So you really want to get out numbers, quantities. And that means you have to have a clear idea of how you measure something. And that's a reliable method of observation. And reliable really means that you can get quantities out of it. Yeah? Otherwise, you do not have the physics standard of testability. That comes from this method of observation. So I would say these are really the 3 points that you should check off your list. Is it clear what the object is? Are the external conditions well controlled? And can you observe the result reliably? Okay? So if you wanted to make a checklist for physics, I'd say that is my checklist. And now you could go back throughout the lecture and just see how every field of physics has satisfied this checklist in a different manner. It's not always the same. You can also go to recent research and look whether this is actually satisfied. There are actually fields of research where I'd say that this is not fully satisfied anymore. And that can be a problem. That can be work in progress. Right? So we actually recently often don't know what the limits of our knowledge are because it's work in progress, and these criterion are really critical. The lecture started with the motion of planets because that's actually the best example. The one where everything can be ticked off very quickly. The planets are recognizable objects. So it's unambiguous enough. We can agree on the planets. We see them. We see them, and that's already criterion 3. Because we can actually get the angle at which they are in the sky, right? Just by seeing. So we see them at positions. And the positions only depend on time. Time is actually an external condition when you think about it, because we determine the time here on Earth, and we just relate this time which we know about here on Earth to the planets. You might say, of course, it's also a kind of planetary motion because we use the rotation of Earth to keep tracks of days, and ultimately, of course, the motion around the sun to keep track of years. Nevertheless, time serves as an external parameter. And that makes the list complete. And the rest is data analysis. And in fact, Kepler's result of planetary motion is the prototypical result where observation to theory really worked. So Kepler identified mathematical patterns in the time series of planetary positions recorded by Tycho Brahe. So he just found the patterns. So can we apply that to all kinds of other fields in physics, right? This would be the prime example that sets the mood. And now we have to develop that step by step. Following the flow of the lecture from the beginning, we'd next come to mechanics. So in mechanics, the objects are movable masses. Now that's actually a bit of a step. We now have objects of everyday life which we can manipulate, we can move them around. They are still clearly visible. So condition 3 is still not a problem. But now the external conditions are rather important because we can manipulate. So what kind of forces act on the objects? That becomes important. So external conditions can vary. Take, for example, the pendulum. So one external condition is the string that fixes the pendulum. And then there is an initial angle. So again, we have basically time as part of the external conditions. And in addition, we have constraints like the string. So we condition the motion which we see as a function in time by initial positions and velocities and external constraints. And that's where we get all our laws of motion from. So the laws of motion are not something that we just know because we are so smart. It's obviously a pattern that we see in the world around us. So laws of motion are geometric patterns in the observed data. And here the principle that starts out physics is that we go from observation to understanding. And that's where you're using theory. So the meaning of the word theory in physics is very specific. It is actually the road from observation to understanding. And it's not very fuzzy, it's very precise. And this is actually a kind of summary of this idea that you can connect human experience to mathematics. Okay? So I hope this gives you a bit of an idea of what the experience of physics is, because that's the main topic of the whole lecture. That's the whole goal, to develop a kind of understanding and idea of what the experience is. I therefore start by putting that in a box, because we need it later. So, you might remember from the whole flow of the lecture that also it was quite turbulent and quick. There was a bit of a transition from the mechanics to the thermodynamics with the optics in between that concerned phenomena. And I told you about the principle of doubt. Now, the principle of doubt is really a kind of critique of the method of observation to understanding. And it's an important one. It's a big part of science. So, the reason for the principle of doubt is that it is very risky to just interpret patterns. The observed patterns are not also the observed patterns are not always so easy to understand. And this is an understatement, because you should realize the Kepler orbits were not easy to understand either. So whatever is easy to understand, right? But the criticism here is in planetary motion, you have a very direct connection to geometry. So at least you could basically say the motion of the planets must be a geometric pattern of some sort. And that's not always so easy. Finding the pattern is even harder, but it's just assuming that there is a pattern is sometimes a problem. That was the problem in thermodynamics. Because thermodynamics is about something that you don't directly see. It's inside the system. So you have internal states, whatever that means. So that's more difficult. How do we do that? We start out with a fixed quantity of material. That can be difficult, but we can use the weight maybe or other criteria to get a quantity fixed. And the conditions now become super important. Here we need the concept of temperature, pressure, etc. And then we need something that we can still observe. And we observe heat transfer. And normally the heat transfer is measured through the temperature change. So we have to be very careful that we don't do anything wrong here. Easier to see is the expansion and every expansion does work PdV. So here the observation becomes a complete process. And the reason for this complication, the observation is now not so obvious, has a lot to do with the fact that thermodynamics is about internal states of the object. So it's very indirect now. And indeed, thermodynamics caused a lot of controversy, and there's still some problems, as I told you, about statistics. So the idea is that thermodynamic states can be controlled by external conditions, right? And that seems to work well enough, so we can say it's scientific and objective. But it's very interesting that it's not obvious what the microscopic reason is, because we, at first at least, cannot look inside. So if your idea is that physics is just knowing what the reality is, here's a problem. That is a counterexample where physics is clearly not knowing what the reality is, but concerns external relations without any clear knowledge of the internal processes. So here you see basically how the gas law appears with certain measurement errors. And this is an experience that you can reproduce. And it doesn't immediately give you an explanation. You just see that the law holds. So here in thermodynamics, you see a shift of the focus of physics. So it's not directly observation to understanding. Observation plays a big role, but observation is possible because of control. So you start by varying the external conditions, like the temperature, like maybe the pressure too. And I'd actually add this to this box, right? So keep the box in mind. You have the box in front of you still, because now I'm getting to another box. And it will appear in the same place, so maybe I should just leave the box, the empty box. So thermodynamics explores the effects of changes in pressure and temperature. On voltage, on volume, sorry, on volume V, and on internal energy U. So we have a control. You could call it the cause. And then you get an observation, which is here the effect of the cause. Now that is the typical structure of experiment. So very importantly here, you can now manipulate the object from the outside, and you try to find out new things by exploring the different reactions that the object shows to the various methods of control that you now have. This is very much the experimental method. So this is why at that point I was also mentioning the principle of doubt. Because the way to find out things when you doubt them is by increasing your experience through the experiment, right? And that is one idea of what the scientific method is. It's the empirical method. And the empirical method is extremely powerful when your understanding and knowledge of the object is not quite complete. So it dominates fields where the details are yet unknown. So I actually have now two approaches, right? One takes you directly from observation to understanding because it's very clear what you're seeing. And the other requires you to play around a bit with the control parameters and to see relations between things that you might not fully understand. And there's actually a third side that completes a triangle. Electromagnetism introduces this side. It originated from the empirical observations of cause-effect relations. So it's actually originally very empirical. Only, as I mentioned in the lecture, these relations are extremely reliable, more than you would normally expect. Going back to our original list of points that we should tick off and basically check. We find a universal set of laws by setting voltages, right? And the result then is currents. That requires us to measure voltages and currents, which we eventually can. And when we can measure voltages and currents, these are our physical objects. So this is non-trivial because originally electromagnetism was developed using this procedure. But once the physical laws are clear, it is convenient to think of the voltages and currents as the object. And that's a big step forward because you would not immediately think of currents and voltages as objects. But they're so well controlled and so easy to measure with precision that they make very good initial objects. And then the shape of the conductor becomes an external condition. And that's the circuit. Of course, the word external here is a bit surprising because you'd think the circuit is pretty much enclosed, it's inside. But external here means the conditions that have an effect, the conditions that shape the phenomenon. When you think that the currents and the voltages are objects, the conductors in the circuits become external conditions. And then you observe the conversion of energy. And that's the essential point. And this controlled and observable conversion of energy that is really the characteristic that we want. And that gives us technology. What is interesting here is the key point is not anymore finding out something, but we were actually now going from our new understanding, which we discovered through the empirical method, to an application. So we start out from understanding now. And the goal is control. And that's technology. You could say here, understanding becomes design. And control is a device. When you look at modern science, you find a lot of that. And by now, the distinction between that and science, between technology and science, is not very strong anymore. It used to be much stronger. There was a big debate about the justification of putting this into science. However, for simply practical purposes, if you look at what physicists are doing nowadays, it becomes clear that a lot of it is this. We are more and more also developing devices, and it becomes a part of what modern science is. So the goal of the lecture is to explore a little bit what that means in society, what that means for us as human beings. And that is why this train of thought is rather important, and why we should actually put all of this together into one concept and one picture. The reason why physicists found it very natural to develop technology has to do with the empirical method and the fact that in order to find out new methods of control, you actually need the technology. So ideologically, you could say there was a separation, but in practice, there was not. Physics emerged from the application of technology. And that's there from the start. But in the beginning, it was very much clear that the technology was the tool to observe. Optics is the best example here, right? Optics is initially the tool of observation. And this greatly enhances our ability to quantify phenomena. By now, of course, we have gone a long way, and all measurements tend to be electromagnetic, at least at some point. So the circle has really closed completely. When you think about recent events like the gravitational wave detection, that's actually a fascinating example of this. Right? Yeah, you can see that, right? So this is super fascinating. The whole effort of new technology that has been put in to detect gravitational waves is amazing. And every piece of that is by itself its own physics. So you have the lasers, you have the quantum mechanics, and even the mechanics, because you have to control huge mirrors. And the object is here, just the gravitational wave, which is a mysterious object that really exists only on the scales of space, of space in a vastness that we find very hard to imagine. So as I told you, the gravitational wave we saw with this kilometer-long interferometer really came from the edge of the universe, from the earliest stages. So that is quite amazing. It does go together somehow. And that is why I would like to summarize all of this in one triangle. And maybe for personal preference, I like to put understanding on the top. And technology is a product of understanding. And it permits to have more control, which gives us many new experiments which lead to observations and back to understanding through theory. So there you have physics as a cycle that involves all of the parts. And I would say that it's normally best to have a balance. So again, when you look at the gravitational wave detection, that's an observation that was made possible through methods of control that were actually derived from an understanding of various fields of physics, from optics to quantum mechanics, and all of that based on theories that came from very, very precise observation. And when you follow this circle back, you see that all of the new results in science depend on a lot of previous work. So it's really like the comment of Newton that we have seen farther than giants because we've been standing on the shoulders of giants. Or I would really rather like to think of it more as many, many people which don't actually have to be individually large because it's our common history, it's our common heritage. So I think that we should experience science as part of our heritage. So I hope that by telling you about these methods and about the way that physicists think, I have brought you a little bit closer to this idea. So it usually gets quite a lot. There is always too little time in any lecture to sit back and relax and think about what it means to us, right? So of course it's a beginner's lecture, so you are just confronted with a whole lot of material. I was motivated to talk about this today because it concerns the way we experience things. And it's not something you should just learn in terms of formalisms, because there is really no formalism here. I've just tried to divide my world of experience up into pieces that you can think about. So we are now here in this lecture entering a little bit into philosophical territory, right? I'm wondering whether you have some ideas or questions that fit into that, because there's certainly many, right? So it would be a bit of a question. Do you have any kind of experience of science that you find is connected to this kind of relation?